Okay, hi everyone, and welcome to the video. So today I'm going to be talking about this problem that you can see on screen. It's a problem concerning special relativity, and it's one that I covered during my undergraduate study of physics that really helped me get my head around the topic. Now, since you've clicked on this video, I'm going to assume you have a basic understanding of special relativity, but don't worry, I'm still going to explain everything fully. I'm just assuming that you know, for example, what length contraction is, time dilation, etc. So let's just set up the problem. As you can see from the diagram, we have two rockets, rocket A and rocket B, and they have a rest length L0 equal to 1 meter. So in this problem, they're both travelling towards each other along the x-axis, but they're slightly offset in the y-axis or in the y direction to avoid a head-on collision. Each rocket sees the other approach it with a speed u, as written here. According to an observer on A, when the tail of B passes the tip of A missile will be fired from the tail of A at B. Now we know that this missile will miss B due to the length contraction of B as seen by A. However, what we want to know is if we analyse the situation in B's frame, will we get the same result? Now, don't worry if you didn't follow all those A's and B's. I'm going to go through all of that again, going through in a lot more detail, so don't worry about that. Now, to set up the problem, we have two definitions here of initial position and time. The tip of A passes the tip of B at time 0, position 0, and the tip of B passing the tip of A times 0, position 0. So this is just their initial positions in time that help us set up the problem. Just in case you aren't familiar with this four vector notation, the initial entry here, the 0, refers to time, and the other one is a position vector. So that's the 3 position. So basically that 0 vector is equal to 0, 0, 0. Okay then, in order to do this problem, we need to consider 4 key events in frame A. Number 1, tail of B passing tip of A. Number 2, missile being fired. Number 3, tip of B passing tail of A. Number 4, the two tails passing each other. So just a couple of things also to consider while in the frame of A. So for an observer in A, due to length contraction, the length of rocket B is going to be equal to, length B we'll call it, it's going to be equal to L0 divided by gamma, where the gamma factor is given by 1 over square root 1 minus u squared over c squared. The same gamma factor that comes up all over special relativity. So let's start by calculating number 1, which is the time and position that the tail of B here passes the tip of A here. As I previously said, the length of B for an observer in frame A is L0 over gamma. And so using time is equal to distance over speed, the time taken for the entire length of B to pass the tip of A, with B moving at speed u, is going to be equal to distance L0, so it's travelling this distance with a speed u, which gives you L0 over gamma u. Now for the position, as previously defined, the tip of A is at the origin of its coordinate system, so the position is just the 0 vector. So this gives our 4 vector for number 1 as L0 divided by gamma u, 0. Next, number 2, where and when the missile is fired. Now, this is easy because this is given through the description of the question. We know that the missile is fired from the tail of A, and we know that the tail of A is at minus L0 because A is L0 meters long. So position minus L0. For the time, we also know that when the tail of B passes the tip of A, which is what we previously worked out, the missile is fired. So the time is again equal to L0 over gamma u. And that gives our 4 vector L0 over gamma u minus L0. That was an easy one. Now we're going to do number 3, where the tip of B, let's go back to the diagram, the tip of B is now passing the tail of A. Now this one's slightly different. For an observer on A, B has to travel the entire length of A, which to an observer on A is L0. So using the same T equals D over S, or distance divided by speed, the distance this time is simply L0, not L0 divided by gamma. And the speed is still 1 over u. So we get a time of L0 over u. Now the position again, we're discussing something happening at the tail of A, and we know the tail of A is at minus L0. So the position is just that again, leaving us with a 4 vector L0 over U minus L0. Finally now, we're going to consider number 4 when the two tails pass each other. We now already have all the information we need for this. We simply need to combine the 2 times of the tail of B passing the tip of A plus the tip of B passing the tail of A, because that corresponds to the entire length of B passing the entire length of A. And we're considering a position in frame A at the tail of A, so we know the position again is minus L0. So I'll just write that out. Time is going to be equal to L0 over gamma U plus L0 over U, which equals 1 over U L0 over gamma plus L0. And the position minus L0 again. So that leaves us with a 4 vector 1 over U L0 over gamma plus L0 and minus L0. So that's all the 4 key events for an observer in frame A. So now we want to consider, will this missile actually hit B? So if we first look at the time that the missile is fired, which we previously said was L0 over gamma U, and compare this to the time that the tip of B reaches the tail of A, we'll call this T1. So the time that the tip of B reaches the tail of A, that we also worked out previously, was L0 over U without the gamma factor, L0 over U. Since gamma is greater than 1, this implies that T1 is smaller than T2, or T1 happens before T2. So this means the missile fired from the tail of A before, that's important, before the rocket B reaches A's tail. So therefore the missile misses B. So just to clarify, the missile is fired from the tail of A, but rocket B is not at the tail of A yet, which means the rocket simply misses B. Now we need to consider frame B. So this frame moves with velocity minus U relative to frame A. Seeing as this is a moving frame, we need to consider the Lorenz transformations of the time and position coordinates to be able to work out times and positions in frame B. The time transformation is given by this expression. Ct prime is equal to gamma Ct minus gamma beta x, where beta is just the ratio of U to C. Rearranging this, we find that T prime, or the time in the prime frame, which in this case is B, is equal to gamma brackets T plus U over C squared x. Now for the x coordinate, we have that x prime is equal to minus gamma beta Ct plus gamma x, which you can then simplify into gamma brackets ut plus x. So those are our two Lorenz transforms, time and position coordinates, which we'll need to calculate the 4 vectors in this new frame. Once we have these transformations, again, we're going to consider 4 key events. Number 1, the tip of A passing tail of B. Number 2, the missile being fired. Number 3, the tail of A passing the tip of B. And number 4, the two tails passing each other. Okay then, let's get on with number 1, which was the tip of A passing the tail of B. So, this is occurring at the tail of B, obviously, and we know that from the question, this is at x is equal to L0 because the length of B is L0. That's easy. And for the time that this occurs, the tip of A must travel the entire length of B at speed u. We've done that before already. Time equals distance over speed. Distance is L0. Speed is 1 over u. L0 over u. Easy. 4 vector L0 over u. L0. Simple. Now next up is when the missile is fired, and that's probably the trickiest one, but actually when you think about it, it's not that hard at all. So we want to think about, from an observer in frame B, the time and position that the missile is fired from the tail of A. Now to do this, we need to employ our Lorenz transformations. So for the time one, we had that T prime is equal to gamma T plus U over C squared X. And then T and X are the times and positions of this event, but in the unprimed frame. So if we look back to where we worked them out previously, we had here L0 over gamma U and minus L0. So if I just copy that, these are the times and positions that the missile is fired in frame A. So we keep that there. So for frame B, we can work out T prime by simply plugging this in. So we have gamma L0 over gamma U plus U over C squared times minus L0, which gives us L0 over, L0 over U minus L0 U gamma over C squared. That's the transformed time coordinate. Now for X prime, as we previously said, we had gamma U T plus X. And simply plugging in values again, we have gamma U, T up here we had L0 over gamma U plus minus L0. And this simply cancels down to L0 minus gamma L0. So our final 4 vector is L0 over U minus L0 U gamma over C squared, L0 minus gamma L0. Next, number 3, which is the tail of A passing the tip of B. So in the frame of B, A has now got a length of L0 over gamma due to length contraction. So the time taken for the entire length of A to pass the tip of B whilst moving at speed U is given by T equals L0 over gamma times 1 over U, which is L0 over gamma U. And this event is occurring at the tip of B, which is defined in the question at the origin at x equals 0, so that's our position, which gives us a final 4 vector of L0 over gamma U and 0. And finally, number 4, when the two tails pass each other. As we did this before, you simply add the two times that we've already worked out, which are L0 over U and L0 over gamma U. And the position, we're considering the tail of B, which as we previously knew was at L0. And that gives us our final result that we need. Now, we actually want to answer the question we set out to answer, which was, will the missile still miss in frame B? So, to work this out, we need to compare 2 times. Number 1, the time the missile is fired in frame B. We'll call this T1. And the second time we need to consider is the time the tail of A passes the tip of B. We need to consider this time because if the tail of A hasn't reached the tip of B by the time the missile is fired, then the missile won't hit B. So if T1 is less than T2, this is T2, then we know that we have agreement across both frames. So T1, time the missile is fired in frame B, is this long formula here, L0 over U minus L0 U gamma over C squared. L0 over U minus L0 U gamma over C squared. And T2 is only L0 over gamma U. Now this might look a bit challenging to work out which one is bigger, but I'll show you a quick trick. T1 can be rewritten in the following way. Gamma squared U squared over C squared. And now this factor here, gamma minus gamma squared U squared over C squared, through long algebra and substitution of beta equals U over C, can be shown to be equal to this. I could show you the algebra, but I think if anyone is still here, they would no longer be. I think they'd either end their lives or God knows what they'd do. I don't think everyone would be watching that algebra, so yeah, I'll just give you the result here. And this is now less than 1. And therefore, T1 is less than T2, which means the missile is fired from A before B reaches A. So we have agreement across the frames, which is good, because otherwise I think special relativity might be wrong, but we have agreement across the 2 frames, so everyone's happy. Bob's your uncle. I hope that was clear for everyone, and I hope you enjoyed it. If there are any questions, please leave them in the comments, and please feel free to let me know anything I could have explained more clearly or anything you just didn't like. Just let me know some feedback in the comments. Subscribe. Bye-bye.